Welcome to an introductory lesson on slope. We're going to get started right away to build you a strong understanding. Here's our first warm-up question. Which of these inclines is steeper? How do you know? Take a second, pause the video if you need. Okay, so using these same pictures, I want you to try and describe to yourself what steepness is. So you already said which is steeper. Now, what is steepness? What are we talking about when we say something is steep? Final question here, which is steeper and why? This is probably the easiest one. My students love this question. The steepness is the same, and that's because these inclines are at the same angle. If we imagine there are right triangles here, okay, we can focus on the angle in the bottom left or bottom right corner to get at the angle of the incline. So if I take the picture away, we have two of the same right triangle. They line right up. These are congruent triangles. What is the same about these triangles besides the steepness of the hypotenuse? And when I say hypotenuse, I'm referring to that diagonal side, right? This side, this side. So besides the steepness of the hypotenuse, what is the same? Okay, the height is the same and the base is the same. Because these are congruent, we know that the height and the base have to be the same. But let's imagine we're going to construct similar triangles, okay? Do you think they will have the same steepness? Let's find out. So similar triangles are related by a scale factor. We're going to use 2 as our scale factor. If you don't understand similar figures, you should still be able to follow along with this. It's just going to help us visualize. So we're going to double the base and double the height. And we're going to fill in a triangle there, but before I put it, I want to ask, will the larger similar triangle have the same steepness as the smaller triangle? Yes, right? That angle of incline is still the same. So although the bigger triangle has a hypotenuse that covers a greater distance, it's at the same angle. The steepness is the same. If you roll the ball down, it wouldn't hit a bump here. The steepness stays the same. It would roll smoothly down. So we can use similarity to understand steepness. Similar triangles have equivalent side length ratios. That means steepness can be represented using this ratio. All right, let's imagine our smaller triangle had a base of 1 and a height of 3. If we apply our scale factor of 2, you can see that our larger triangle would have a base of 2 and a height of 6. So the scale factor relates corresponding side values across triangles, right? 3 times 2 became 6, 1 times 2 became 2. Now, similar triangles also have the same ratio of sides within a triangle. So instead of going across, we can go in the triangle. Let me show you that. 3 divided by 1. Okay, I'm making a ratio between the sides in the same triangle. That's 3. If I go to those same corresponding sides, right? Green over red, 6 divided by 2, I also get a ratio of 3. So it's not a coincidence that these similar triangles have the same steepness and the same ratio of height to base. The ratio of height to base is the steepness, and it also is slope. So let's go from here with some more examples. Now we can look at these two triangles, okay? Which triangle is steeper? The red one is steeper, right? That angle is really a tall, high angle. So this is the steeper triangle. Some students might say the blue triangle is steeper, but that's incorrect. It is taller and bigger, but it has a smaller ratio of height to base, so it doesn't go as high as it moves over. The hypotenuse goes up less relative to the base. And we can also see that this angle is smaller. Now let's use some numbers. Now remember, slope is steepness. It's the ratio of the height to the base. So I take the height, I divide by the base. 2 divided by 1. There's a slope of 2 for this hypotenuse in this triangle. Over here, a height of 3 divided by a base of 6. We simplify that and we see the slope is 1/2. Our red triangle has a much greater slope value, right? 2 is greater than 1/2, and that proves that the red triangle has a steeper hypotenuse than the blue triangle. Another example. I have a base of 4 and a height of 5 for my green triangle, and then it's switched for my pink triangle, a base of 5 and a height of 4. So we're going to calculate the slope. So over here, I take the height, divide by the base. 5 over 4 is 1.25. Then for the right one, I do the same thing. Take the height, divide by the base, and I get a slope of 0.8. This time I chose to use decimals because you can easily see that the slope of the green triangle is a greater value than the slope of the pink triangle, meaning that the hypotenuse of the green triangle is steeper than the hypotenuse of the pink triangle. So by looking at these triangles, we have learned that slope is steepness, which is the ratio of the height to the base. Now, in other words, I could say it's the ratio of the vertical distance, which corresponds to the height, to the horizontal distance, which corresponds to the base. And as a definition, I'd say slope is the ratio of how high we go, right, how much we rise, compared to how far we go, how much we run. So now we can use this information to work on a coordinate plane. So I have a triangle here, and you can see that instead of writing height and base, I wrote rise and run. So rise refers to the height, run refers to the base. From A to B, we rise 3 up and we run 1 right, okay? You take the height, divide by the base, take the rise, divide by the run, and you get a slope of 3. So having a right triangle positioned along the grid lines underneath our line segment AB made it super easy for us to see that the segment AB has a slope of 3. Now, you can draw a right triangle, aka a slope triangle, along any line to find the slope. This is what I was just saying. Now we get our example. If we place one corner of our triangle on the red point and another on the blue point, we can count grid lines to find the height and the base, okay, the rise and the run. So I could easily just see that to go from red to blue, I have to go up 2, and there's a 2 on the axis, over 1. There's a 1 on the axis showing me this. See, height of 2, base of 1. Then we would use our formula, height over base, rise over run, to see that this segment from red to blue, this line, has a slope of 2, and that's consistent anywhere on the line. We're going to prove that by making the same triangle somewhere else. So look, I have the same horizontal and vertical change, the same height and base from the blue dot to the purple dot. So over here, there's also a slope of 2. So this whole line has a slope of 2. And that should visually make sense to us because we can see the steepness or the slope is the same all along this line. Now, we're going to make a formula for slope, okay, so that you can just plug in values when you're given them. So we have a height, a vertical change of 2, and a base, a horizontal change of 1. What if we only had coordinates for these 2 points? So we didn't have a graph, or we just didn't want to count the grid lines. What could we do? Well, we can figure out this height value and this base value by using subtraction. So I look at the height of this triangle and I see I go from 2 to 4. How do I find the difference between 2 and 4? Well, I would subtract, do 4 minus 2, and then I could see that my height value is 2. Same thing for the base. I look at the base and I see that I go from 1 to 2. The difference between 1 and 2 is 2 minus 1, and we can see that the base is 1. So, in other words, to find the height, we subtract y coordinates, and to find the base, we subtract x coordinates. So here is the formula. Slope is rise over run, which is also height over base. And to find the rise, you subtract the y coordinates. Same thing with the x coordinates. Sometimes students get confused about these subscripts here. We just use them to distinguish between the 2 points. So x1, y1 would be one of the points, and x2, y2 would be one of the other points. So we're just differentiating between the coordinates. If we kept everything as x and y, we wouldn't know which point we are referring to. When we plug into our slope formula, we just have to make sure we are matching up our coordinates. Take a second and think of the coordinates of the blue point. Yes, it's 1, 2. Now you can take a moment, find the coordinates of the orange point. 2, 4. Okay, slope is rise over run. It's the change in y over the change in x, or the height over the base. So we're going to start with one of the y values, right, one of the y coordinates, and subtract the other. So I choose to do 2 minus 4. I'm doing blue minus orange. Now I'm going to do the same thing with my x coordinates, blue minus orange again, 1 minus 2. So when I fill in my formula, I have the difference in the y coordinates over the difference in the x coordinates. And you can see that my blue coordinates are matching, right? They're lining up, and my orange coordinates are matching. So these subscripts in the formula only tell us that we have to line up our coordinates, right? If I do blue minus orange, I then also have to do blue minus orange in the denominator. I wouldn't want to crisscross. That would give an incorrect result. Now we are ready to do an example using both methods. So I have a pink line on my coordinate plane, and we're going to find the slope of this line. First, we could draw a slope triangle anywhere along this line, and I want it to line up nicely with the grid lines. If I see I hit the origin, right, 0, 0, I'm definitely picking that. And I'm going to look around, and I see right here I hit the intersection of my grid lines, so that's going to be the other corner of my triangle. So here's where I'd position my triangle. I know that m, slope, is height over base, and I can see that I have a height of 1, a base of 2. So if I divide my height by my base, I get 1/2. And that's the slope of this line. It's that easy. Now we can try using our formula. So we'd find any 2 points on the line. Now I could pick the vertices of my triangle, but I'm going to mix it up just a little bit to prove that the slope is the same anywhere, and you can pick any 2 points. So I'm going to pick that blue origin, and then I'm going to use my orange point and pick something further away. There's my formula. The blue point has the coordinates 0, 0. The orange point has the coordinates 4, 2. I showed you right here what the subscripts mean, right? So x1, x1, y1, y1. Okay, I'm going to color code it, but that's what this formula does. It's just so we can keep our coordinates in order. I see my formula, and I see that I subtract my y values, and I did orange minus blue. So 2 minus 0. Then I go to my denominator, and I know I'm going to do orange minus blue again. 4 minus 0. I have orange minus blue in the numerator and the denominator, so I followed the formula correctly. And I can see my slope is yet again 1/2. So our 2 methods for finding slope agree. We can take the height of a slope triangle and divide by the base, or we can use our formula and plug in with our coordinates. No matter where you draw your slope triangle or which 2 points you choose on the line, you will get the same slope value. All right, here are some final notes. Slope is steepness. It's the ratio of the vertical distance to the horizontal distance, height over the base, rise over the run. You can use a slope triangle for height over base, or you can use the formula when you have coordinates. Please leave any questions in the comments. Thanks for watching.